All right, everyone. Thanks for joining the next iteration of the COMSOC seminar. And so today we have two very exciting speakers. But before I introduce them, I would like to give the floor to Omar to make an announcement regarding the flagship workshop of our community.
Thanks, Nisarg. Just a reminder to everyone that registration deadline for COMSOC 2023 is this Sunday. Supposed to be we're hoping for a great program. We have two Nobel laureates. We have Uman and Maskin. We have Itzik Gilboa. We have Sari Kraus. We have some great speakers, of course, from the community. We also, there are still places in the university small hotel, which is quite cheap for anyone interested. So we're hoping for a great program, and hopefully many of the community will come along. And for the Israelis here, students can come free if they give up the free lunch. So I encourage Israeli faculty to send their students, not just themselves as well. So hopefully everyone will come along. That's it. And on to the main event.
Perfect. Thanks, Omer, and thanks, Dominic, for posting the link. All right, so today we have two really exciting seminars. First, we are going to have a seminar by Michal Feldman, who is from Tel Aviv, and she's going to tell us about algorithmic contract design, which is based on a series of two works from a Stock and a Fox. And then we are going to have, as usual, we are going to have the 20 minutes talk, 10 minutes Q&A, and then a 10-minute breakout session. And then we'll reconvene for our second talk by Moshe Babaioff, who is now at Hebrew U. And he will tell us about fair shares, feasibility, domination, and incentives. So this is some of his work on recent work on fair division. And since we are always pressed for time, let me not take too much more time and pass the floor off to Michal.
Hi, thank you very much for the invitation. It's a great audience to present the talk to. Just a short disclaimer, perhaps the topic of my talk is a bit of an outlier here in COMSOC. I hope I can excite you by this topic, and I'm sure there will be many things you can think of about contracts that can be part of COMSOC in the future. So I'll just share my screen. And Omer, I promised to send my students with a sandwich to COMSOC.
We do have a Mensa, they just don't get the free lunch, but they are always invited.
Great. Okay. So I'll just hide it. Great. Okay. So I'll start. I'll just take the time. Great. This is so I'm going to talk. So I'm going to talk about algorithmic contract design, and specifically, as Nisarg said, it's based on two works, with both of them with Paul Dutting, Tomer Ezra, and Thomas Kesselheim. And some of the introductory slides are adjusted from slides by Paul Dutting and Inbal Talgam Cohen. So thanks to them too. Okay, so a bit of introduction, although perhaps this audience does not need a very elaborate introduction. We all know by now that algorithms shape economics and society in many ways, and different applications shape the resources we get and how we get them, the content we see, whom we hire, and in what ways we hire people to do tasks for us, different opportunities we face, and so on and so forth. So this interaction, this very deep interaction between algorithms and incentives that started with the emergence of the internet has many different components to it, this intersection. And for many years, we've been busy with studying algorithmic mechanism design. But in recent years, it started to be very clear that there are many other facets to this very fascinating intersection, like algorithmic information design and algorithmic contract design. And all of these are really at the core of economic design, just looking at the interesting problems from algorithmic and computational perspective. And today's talk is going to concentrate on algorithmic contract design. So what does it mean? We use contracts when we want to incentivize strategic players to put in effort by paying for the effort's outcome. And now let me say paying is not necessarily in monetary units. It might be, for example, a teacher who wants to incentivize the students to work hard, and then incentives go by a grading scheme, for example. So examples are any outsourcing operation to freelancers, or as I said before, getting students to learn, and many, many examples, tons of applications where this is very relevant. And I would say that the defining features of a contract situation, the first one is that the action of the agent cannot be directly observed by the principal. And the second one is limited liability, which means that the principal is the one paying the agent. And this contract design problem is also known as a principal-agent model. So we have a principal and an agent, and the principal wants the agent to put in effort. And also sometimes it's called hidden action, namely that the action cannot be directly observable by the principal, and this is really the core problem of these problems. It's also called sometimes adverse, moral hazard. So all of these refer to this very inherent problem that we all face. And now as modern applications grow in scale and complexity, they move online, they are huge, they're data-driven, they move to the internet. So all of these problems are really growing in scale and complexity. So for example, if before we just outsourced the task to a freelancer one-on-one, and now we have huge freelancing platforms where we can outsource our many tasks to many agents in various combinatorial ways. The same about teaching. We used to teach a class in a small classroom with maybe 200 students considered to be a lot, but now we are running these massive online courses. And again, we need to find good ways for incentivizing the students to learn. So this short introduction is just here to say that the algorithmic and computational perspective to contract design is timely and relevant. And indeed, this is an emerging frontier in algorithmic game theory with two recent workshops, both in Stock 22 and DC 22, and many. This is just a partial list of papers that appeared in this literature. So, and as you can see, it's very closely related to the way algorithmic mechanism design evolved. So algorithmic mechanism design evolved, and then we studied simple versus optimal mechanisms and combinatorial auctions and auctions for social goods, et cetera, et cetera. Now you see all of this literature growing in these different directions and others. So for example, we study simple versus optimal contracts, and we study different ways in which the contracts are becoming combinatorial through different components of the model. Contract design for social goods, very beautiful papers on this topic. And also there are papers more recently on the interaction of hidden information, which is what's lying in the base of mechanism design and hidden action of contract design. So what happens when we have both hidden action and hidden information, and how not, what happens in the intersection with learning? How can we learn contracts? What's the connection between learning and contracts? And today I'm going to focus on two different papers on this big topic that I call combinatorial contracts, which cover a lot. And before going into this direction, let me just show you the very simple, non-combinatorial vanilla model of principal agent. So the story goes as follows. We have an agent the agent chooses an action. You can think about it as shirk or work hard. The action incurs some cost. Every action A incurs a cost C of A. And the action also induces some reward with probability F of A. So you can think of A as different levels of effort, for example. And as the agent induces more and more effort, the task for the principal succeeds with higher probability. So F of A is the probability that the project succeeds. And this project gives, if successful, it gives a reward of 1. 1 is just normalized to 1 to the principal. So up until now, the agent has absolutely no incentive to work. Working entails a cost to the agent and a reward to the principal. So why work? So then this is the point where a contract comes in. In order to incentivize the agent to work, the principal defines a contract, which for now is just a scalar alpha between 0 and 1, which specifies what fraction of the reward goes from the principal to the agent if the project succeeds. Namely, the expected payment from the principal to the agent is alpha times F of A. With probability F of A payment of alpha goes to the agent. So the principal pays alpha FA in expectation, the agent receives alpha FA in expectation. And so the expected utilities of the two players are the following. The expected utility of the principal is 1 minus alpha, which is the remaining reward the principal is left with after paying the agent, times the probability that the project succeeds, F of A. And the expected utility of the agent is alpha FA. This is what the agent receives in the event that the project succeeds, which happens with probability F of A, minus C of A, the cost of the action. Now, I want you to note that the cost of action A, of the chosen action, is incurred by the agent in any case, but the payment comes in only with probability F of A that the project succeeds. And we see here the defining features. The action is hidden by the principal, so the principal cannot condition the payment on the action of the agent, only on the final outcome, whether the project succeeded or not. The outcome is stochastic with some probability that depends on the action the project succeeds, and limited liability means that alpha must be at least 0. It cannot be negative. Okay, and now let me go to the different sources of complexity in contract design that can occur. The first one is multiple agents. Sometimes the project is not carried by a single agent, but by a team of agents. And then we are looking at the different delicate dependencies of how the different actions carried out by the agents induce a final outcome. This is one aspect. The second aspect that I'm going to talk about today is what happens when we still have a single agent and a single principal, but there are multiple actions, and the agent does not just choose one action out of this set, but the agent can choose any subset of these actions. Which is usually the case where an agent has many actions she can take, and she just chooses a subset of them. And here the question is how the combination of the actions chosen by the agent determines the final outcome. Let me just say that the complexity in contract design is not limited to these two sources. This is just going to be the focus of today's talk. Okay, so let me start with the multiple actions. So here is the model. We have a single agent, and there is a set, capital A, of n different actions, from which the agent chooses a subset, S. The cost of every action is again denoted by C of A, And let us assume that the cost function is additive, meaning that the cost of a set of actions is just the sum of the cost of the individual actions. And now we move to the combinatorial aspect of this model. There is a function f which maps any subset of actions chosen by the agent to a probability of success. So f of s is the probability that the project succeeds when the agent chooses the subset of actions s. And the whole point here is that this function f is not necessarily additive. Okay, so if not additive, what is it? It can be any type of this very beautiful hierarchy of functions that we came to know by the seminal paper of Lehman and Nissan. Let me not define to you in this short presentation all the different classes. Those that I'll need, I'll say a few words about them. And the reward is before we normalize it to 1 for success and 0 for failure. Okay, so like really briefly, submodular function is the class of function that has diminishing returns, namely the marginal contribution of an item, of an element, is decreasing in the set that I already have. And subadditive functions is the frontier of substitutes valuation. It just means that the sum is smaller than the f of a union of S and T is smaller than the sum of the separate ones. Good. So let me just repeat the model. Very simple model. N actions, the agent chooses just a subset of actions. The cost of the actions is additive, but the reward is not necessarily additive. And our main result will be for a class of functions called gross substitutes, which I'm not going to define due to lack of time. Let me just say that this is an important subclass of submodular functions. It includes important classes like additive, unit demand, matroid functions, and others. And it's important because it is known to be the frontier for important computational and economical problems. Good. So let me skip this. And here is our main result. We have a polynomial time algorithm for computing the optimal contract in gross substitutes functions. I think somehow I didn't see the definition of the optimal contract problem. Okay, yeah, sorry, I skipped this. So let me just go over. This is a very important slide. At the bottom, you see the problem that we study in these papers, which is the optimal contract problem, which you can think of as a two-stage optimization problem. So we are always looking at these problems from the perspective of the principal. The principal wishes to maximize her expected utility, which is 1 minus alpha times f of s. So the problem is to find the contract, namely alpha, that maximizes 1 minus alpha times f of s, where s, in turn, is the subset that maximizes the expected utility of the agent, because the agent sees alpha, the contract, and decides what subset of actions to take. The subset of actions the agent will take is the set S that maximizes alpha times f of s minus c of s, his expected utility. Okay, so from the perspective of the agents, we always fix alpha for a fixed contract, alpha. What's the subset of actions that maximizes his utility? And the principal wishes to maximize her expected utility, knowing that the agent will best respond. Okay, any questions about the problem? Good. So now I can move to our main result. And our main result is that if the function f is gross substitutes, then we have a polynomial time algorithm for computing the optimal contract. In contrast, if we move one level up in this hierarchy to submodular functions, which is the class of functions that has decreasing marginal contribution, then the problem becomes NP-hard. So in some sense, growth substitutes is a frontier of tractability for the optimal contract problem. Let me put a small asterisk here, because in a few slides, I'll say a few words about this frontier. Those of you who are familiar with the work of Nissan and Segal for computing welfare maximization in combinatorial auctions, or the very seminal work about market equilibrium existence, know that growth substitutes is also a frontier for these two very important problems. The interesting thing is that these three problems, so now we have a third problem for which growth substitutes is tractable, are three very different problems. For once, I mean, okay, two of them are computational. The third one has nothing to do with computation, at least on its face. It's totally an existential problem, market equilibrium existence. And still we see that growth substitutes, this structure of growth substitutes is very important. Let me give you a short geometric intuition for what's happening here. So what we see here is, first of all, from the agent's perspective. So here we see on the horizontal axis, we see alpha, the contract. On the vertical axis, we have the agent's expected utility, which is alpha fs minus c of s. And the very simple observation is that the agent's utility is linear in alpha. So what we do for every set of actions, we draw a linear curve which represents the agent's expected utility for the given alpha, for the given set of actions as alpha grows. And what determines the agent's behavior is the top envelope of this graph. So for example, up to this alpha, the agent will take no action and then take action 1, then take actions 1 and 2, then actions 1, 2, 3. As alpha increases, as the agent gets more and more payment for working hard, he works harder and harder. This example that is drawn here is for a very simple F function, reward function, which is additive. So here both the cost function C and the reward function F are additive. And what we see, which is a general theorem here, is that if F is additive, then what we see here is not a coincidence. As alpha grows, in every transition, the agent adds one more action to the actions already taken. So what we see here is empty set 1, 1, 2, 1, 2, 3. So we have a very simple and smooth structure of this agent's response. Good. So this is the top envelope, and this is what determines the action taken by the agent. This is from the agent's perspective. From the principal's perspective, what happens is that in every such region of alpha, the agent's behavior is fixed. We know exactly what set of actions the agent will take. But within every region, alpha increases, meaning that the principal pays more. So we get a decreasing linear function for the principal's expected utility. And this means that an optimal contract will always be a transition point between agent's best response. So, good. So optimal alpha is this transition point, which we call a critical alpha. And this suggests a very naive algorithm for computing the optimal contract, which is the following. Go over all critical alphas and take the best one. For each critical alpha, we can compute what the agent will do. We can compute the expected utility of the principal and just choose the one that gives the maximal one. However, this very naive algorithm requires two things. One, we need to find the set of critical alphas. So every time we have to compute the next critical alpha, we need to understand what's the structure of these transitions. for the simple structure of additive F, this was very simple. Every time one action is added, but more generally for combinatorial function F, these transitions can be crazy. The second point is that we require an upper bound on the number of critical alphas. Even if we can compute the next critical alpha every time, if we have exponentially many transitions, I mean, recall that overall we have 2 to the n different subset of actions. So a priori, we may have exponentially many such transitions, and then this naive algorithm will not yield a polytime algorithm. And what we show in our theorem is precisely that for gross substitutes F, this yields a polynomial time algorithm. Namely, we can find the next critical alpha in polynomial time, and we can bound the number of transitions to be polynomial. By the way, for submodular function F, there are submodular functions F that do have exponentially many critical alphas. This does not still mean that the problem is hard, but it means that this naive approach will not work. But separately, we also show that the problem is NP hard. Okay, let me spend 1 minute on to give you the geometric intuition for gross substitutes function. So here we see an example of a gross substitutes F function. And what we see here is that, as expected, indeed, the transitions are not as smooth as we had for additive function F. For example, we start with empty set, then we have a region where the agent takes action 1. Then it's not the case that he adds action 2 on top of action 1. He replaces action 1 with action 2, removes action 1, and then action 1 comes back. So we have this non-monotonicity thing. So a priori, it's very hard to say how many such transitions we will have. And the key lemma, let me skip this thing about demand queries. The key lemma that that enables our result is showing that at each critical point, if the function F is gross substitutes, one of 2 things happen. Either an action is added to the set S, this is what happened in the case of additive F, or an action from S is replaced by one with higher cost. These are the only 2 things that can happen in transition points for gross substitutes functions. And with this observation at hand, we can just have a potential function argument showing that the number of transitions is at most quadratic. And this essentially gives us a polytime algorithm for gross substitutes function. Yes.
Michal, sorry to interject, but we are a little bit over time. So if it's possible to end soon, that would be great.
Okay, we're okay. Sorry, I didn't realize that. Okay, so let me maybe, would you like me to end now or spend maybe 2 minutes about multiple agents? Your choice.
Spending 2 minutes on multiple agents sounds good.
Okay, good. So let me skip these slides. These slides just show that we can go a bit beyond gross substitutes, but I'll skip those. It's actually nice that I'm going to tell you also about multiple agents, because Moshe Babaioff, who is the next speaker, is one of the co-authors of one of the first papers where we considered this problem actually a long time ago, back in 2006. So here the model is the following. We have n actions. So now the task is performed by n actions. Now the structure of the actions is very simple. So every action is just for every agent, the action is binary, 0 or 1. So exert effort or not. Exerting effort has a cost, CI, for agent I. The outcome is still binary with a reward of 1 for success. And the combinatorial aspect now comes in the function F that maps the individual decisions of the agents of working or not working to the probability of success. Okay, so now it's the delicate dependencies between the effort of the different actions in the team that determines the final outcome. Okay, so let me skip this because I'm out of time, and let me just tell you the main result here. So what we show here, let me also go forward here. Good. So what we show here, so now again, the problem is for the principal to find the right set of agents to contract with. So again, it's a two-stage optimization problem. The principal contracts with a certain set of agents. The principal wants a certain set of agents to exert effort. These agents exert effort in equilibrium, and the combinatorial problem is to find the right set of agents to exert effort that maximizes the principal's utility. And this problem is already NP-hard even if F is additive. And what we show is that if F is submodular or XOS, doesn't matter what it is, some extension of submodular, we do have constant time approximation to the optimal contract problem. However, when we move to subadditive function, we cannot give a better approximation than root n. And with this, let me summarize. I hope I convinced you that contract theory is a very exciting new frontier in algorithmic game theory, where complexity and approximation are important and shed new light on different problems of contract design. There are very interesting connections between combinatorial contracts and combinatorial auctions, even in terms of the computational models and the way we use them, the different structures and classes of functions that are important in these two sets of problems. And maybe the most important problem is that we have still tons of very fundamental problems open. And maybe I'll use this opportunity to advertise a survey on algorithmic contract design that is coming soon, almost done. This is joint work with Paul Duting and Inbar Telgam-Cohen. And with this, let me thank you for listening.
Let's unmute and thank Michal for telling us about algorithmic contract design. Right, so there are a few questions in chat. Bill, do you want to unmute and ask your question about multiple levels of success?
Sure. It seems that your treatment of success is that it's either entire or none. Of course, the quality of the work done by the agent might affect a level of success. And I wondered whether that would have any impact on the overall results. And then Nisar,
yes. Sure, this is a very important question. Indeed, if the outcome is binary, either failure or success, then linear contracts are optimal. There is no other way. There is no way to get a better utility than just with linear contract. So if we move to different levels of success, everything that we said about linear contracts is still holds, but linear contracts are not necessarily the optimal ones anymore.
Thank you.
You're welcome.
Right. Yeah, so that answers my follow-up comment as well. And then, Bill, you have the next question as well. I don't know what this was in context to, but you asked, would optimal alpha still necessarily be critical? I think this was for the growth substitutes, or like the next. Oh, sorry, you're muted, Bill. Bill, you are muted.
No, just ignore this question. It was a follow-up to my own question, really.
Okay, no problem.
Right.
Would you like me to read the chat, or would you like to tell me the questions?
Yeah, I mean, you can read the chat, I guess. Yeah, so Rohit's question is self-explanatory. Unless, Rohit, you want to unmute and add something?
No, just curious about non-monotone probabilities, right? So if adding an action lowers the probability, what would we say in that setting? I was just curious about that.
If the function f is non-monotone.
Yes.
Yeah, in fact, we only considered monotone functions here. So I guess the answer is I don't know. And I suspect that many things can go differently if the function is non-monotone.
I suppose even if the agent is fully generous and wants to help out, even then it's not clear what set of actions to choose anymore. Even that already might be a hard problem. So
yes, it is. And in fact, maybe one thing that is not directly related to this question, but somehow related to this question is, you know, that in one of these problems, we considered multiple actions and we completely simplified everything else, like one agent, but multiple actions. In the second paper, we did exactly the opposite. We considered many agents, but very, very simple action structure, binary, zero or no, effort or no effort. Now in a working paper, we are working on the combined complexity that is introduced by a model with multiple agents and multiple actions. And here, the interesting point is that we may see, I mean, it's not that the function f is non-monotone, but it may be the case that if some agents work harder, it may induce other agents to work less hard because of some free riding issues. And there's some different non-monotonicity, not by assumption, but by just the virtue of how things evolve, become very interesting.
all right, Adrian has the next question, which is what happens if the cost function is super additive?
Okay. This is a wonderful question. So let me 1 second share screen again. This is in one of the slides that I skipped. Okay, you're asking about if C is supermodular.
Yes.
Okay, good. Okay, let me answer a different question because I think it's interesting. Here is another situation that we can completely solve using more or less the naive algorithm that I showed you. And this is the problem where F is supermodular, so very different than the structure we've seen, and C is submodular. Because of course you are right that everything that I said up to now, I only considered C that is additive. And I agree that it's very interesting to study different structures of the function C2, because also the cost function, it's very reasonable that the C function itself is non-additive. So I do not know what happens when C is supermodular. This may be a hard problem, but here is a very interesting case I think that we can solve, and this is the case where F is supermodular and C is submodular.
Right.
And this is in an ongoing work with Yoav Galtzur and Paul Dutting. Yoav is my student.
And the final question is from Peter, which is that here to compute the optimal alpha we need full knowledge of F and C. And is this reasonable to assume? And what if the principal only has rough estimates of these functions?
So
yes,
my intent is to turn it more or less in a learning problem. If the task is iterated and you're facing a number of agents you have incomplete information about, but gradually you start to learn their capabilities and preferences.
Thank you for the question. This is, again, a very fascinating question. And as I told you in one of my first slides, this interaction between contract design and learning is becoming very popular now. And there is a very beautiful paper by Michael Jordan from Berkeley and his students in upcoming EC, exactly about this problem of what happens when you do not know these features and you learn them iteratively. What can you do? So this is one of the papers that study this, and there are others. So this is indeed a very, very interesting line of research that is being taken now.
Thanks.
All right, so those are all the questions that we had for now. So let's thank the speaker again.
Thank you very much.
And now, Dominic, if you would do the honors.
Yes, so we are going to have 10 minutes of a coffee break. And if you like, you'll be assigned to a random breakout room where you can chat to other participants, and see you back here 52 past the hour.
Seems like all right, seems like everybody is back. So let's get on to our next seminar by Moshe Babaioff. He'll tell us about fair shares, which is a new class of fairness definitions for fair division. So Moshe, over to you.
Yeah, thanks, Nisag, and thanks very much for the invitation, and thanks for joining the talk. So this is a joint work with Uri Feige, and it was at EC 22. So the problems that we're going to consider here is the problem of fair division, fair partition of indivisible items, with the goal of when agents have equal entitlement to the goods and without money. So here we have 4 items and we have 2 agents, and we ask what would be a fair allocation of this partition of these items to the 2 agents. So what is fair? So there are 2 approaches. The first one that is prevalent in the literature is the envy-based approach. We try to eliminate or minimize envy between the agents, and there are notions like envy-freeness up to 1 good, envy-freeness up to any goods that were studied, and I'm not going to dive into those. And the second approach that I'm going to discuss today is the approach in which we try to give each agent some values that she deserves or close to it. And I'll call this the share-based approach. So just that we'll be on the same page, let me present the model formally. We have n agents. They have equal entitlement to the set M of M indivisible items. There is no money. Each agent has a valuation over subsets of items. So VI of S is the value of the set S. And we, as usual, we'll assume that VI is normalized and non-decreasing. And in some part of the talk, I'll talk about additive valuation functions, in which the value of a set is just the sum of the values of the items in the set. And we're looking for an allocation, which is the partition of the items to n disjoint bundles when agent I gets a bundle AI. Okay, so Budish has suggested the following notion that is called maximum share to represent how much an agent deserves. So basically, it thinks about an agent that needs to divide the items to 3. So the agent chooses how to partition the items to 3 bundles, knowing that the agent is going to get the worst one of all these bundles. And he will, of course, try to partition them as equally as possible so that the worst one will have the highest value. So in this case, if the Panda has an additive valuation and these are the values of the items, the MMS is 2 because that's the largest you can give to the 3rd bundle in any partition. Okay, so clearly, if the valuations of every agent is the same, then you cannot give all the agents more than the MMS, essentially by the definition of the MMS. But is it possible to give every agent her MMS? So in a seminal work by Kurakawa, Fukacha, and Wang, they showed that when you have 3 agents and additive valuations, then the MMS is not feasible. That is, there are additive valuations over 3 agents. Of course, these valuations are non-identical, such that it's not possible to give every agent her MMS. Okay, so when we think about fairness, we want to essentially guarantee it to every agent. And if the MMS is not feasible, how can we use it as a fairness guarantee? It seems that it's not useful. So we want to define different shares that may be useful as fairness shares guarantee. And then we should think about what is a share and what is a good share. And I'll try to discuss that in this talk. Okay, so let's think about the share landscape. we are all familiar with the proportional share, essentially giving each agent 1/n fraction of the grand bundle. The MMS is another share, but what we want to think about is the space of all shares. We want to define what is a share, and specifically the space of feasible shares. These are shares that we can give all the agents concurrently. So the MMS is not a feasible share. But of course, it's always at least as large as any other feasible share. This is represented by this arrow because, by definition, you cannot give more than the MMS to n agents, to all n agents if the valuations are equal. Okay, so what is a share? So we define a share to be a function that maps the valuation of agent and the number of agents to the share value SVI of n. And we want to share a share function to satisfy two natural conditions. One is independence of items names, that basically says that the share does not depend on how do we label the items. And being realizable means that you can get your share at least when you get all the items. So these are very fundamental, simple properties that you would expect from a share. And note that the share S is a function that doesn't depend on I. Okay, so it's an anonymous function. It depends, it's the same for all agents. And this comes to capture the fact that agents have equal entitlements, and therefore we should not actually discriminate between them when we define the share of the agents. It should only depend on the valuation of the agent and not on the agent identity. Okay, so once we define a share, we can ask which bundles will the agent see as acceptable. So a bundle B is acceptable to I if the value of the bundle is at least the share for the valuation VI. And then you can think about the share guarantee. What is the share guarantee? Is given a share, the agent can consider all the bundles that are acceptable, every bundle that is acceptable, and consider the worst bundles that she might get, and that's the share guarantee. Once you put forward the share, the guarantee that is presented is the value of the least valuable bundle that gives at least the share. Okay, so how do we view the share? We think of a share as a contract between the agent and the allocator. The contract has a context, which is the items and the agents and the class of valuations. And the agent has the right to get an acceptable bundle. That is, he's expecting to get a bundle that gives her at least her share. But the allocator still have the right to choose which acceptable bundle he gives to each agent. So he's not committed to give specific bundle or for a specific function, but rather he only commits to give each agent an acceptable bundle. So the first property ensures fairness because every agent is guaranteed to get at least her share. And the second leaves flexibility for the allocator, for example, to achieve other goals as equalizing as much as possible the leftover value or something like that, or maximizing welfare or other goals. So what are these desired properties from a share? So first, of course, we want the share to be feasible. That is, we want to be able to give the share to all the agents concurrently to satisfy the contracts of every agent. Secondly, agents need to be able to verify that she indeed got a bundle that gives her at least her share. So for that, she needs to be able to compute in polynomial time whether the bundle actually gives her her share, and therefore she needs to be able to compute her share. From the allocator perspective, it will also be good to be able to compute an allocation that gives every agent her share in polynomial time. Third, we want to give the share to give incentives to the agents to be truthful. And we're going to capture that by properties that I'm calling self-maximizing share, which I'll discuss in a few minutes. And this property is different than dominant strategy incentive compatibility. I'll discuss that. But why do we want agents to report truthfully? Because this saves them the bothering strategizing, and also then the allocator have the correct input to use to decide on the allocation. Okay, So we said that we leave the allocator the flexibility to give the agent any acceptable bundle. Now, will the agent report truthfully? We're going to assume that the agents want to maximize her share guarantee. That is, she is aware of the definition of the share, and she's essentially afraid that she will get the worst possible bundles that gives her her share, and she wants to maximize that. So we'll call it a share self-maximizing share if truthful reporting maximize the share guarantee. And of course, what an agent care about is the true valuation. So she measures everything with respect to the truth. So let's think, for example, about the MMS. Truthfulness is essentially if I give the agents the opportunity to partition the items to n bundles, knowing that she will get the worst one, will she manipulate the partition and partition the items differently than the ones that maximize the least valuable bundles? Then it's quite easy to see that there is no reason to manipulate that. But let's consider a different share, which is called the 3/4 MMS. 3/4 MMS is just the MMS times 3/4. So here is an example. We have n equal 2, and we have additive valuation over 3 items with value 100, 80, and 20. The MMS here is 100. Why? Because the best partition is the correspond by itself and these 2 items together. And then the worst bundle has value 100. So 3/4 of the MMS equals 75. Now, if the agent reports truthfully, then it is okay to give her only the cherries, right? Because the cherries have the value of 80, which is larger than 3/4 of 100, which is 75. But the agent actually can manipulate and report values 100, 50, 50. Note that under these valuations, if that was the true valuation, the MMS would be still 100 by the same partition, the correspond by itself and these 2 items together. So 3/4 of the MMS is 75, but now the cherries by themselves are not giving the agent 3/4 of the MMS. So if the allocator wants to guarantee 3/4 of the MMS, he must either give the correspond or give any 2 items, right? He can no longer give just the cherries by themselves. And therefore, the 3/4 MMS is not self-maximizing. That is, truthful reporting is not in the best interest of the agent. Okay, so we have this definition of self-maximizing shares, and we saw that the MMS is self-maximizing. I mentioned that, but 3/4 MMS is not self-maximizing. Okay, so 3/4 MMS, why do I pick 3/4? Because Gargantaki showed that actually 3/4 MMS is feasible. So it is possible to give all the agents concurrently 3/4 of the MMS, but it's not self-maximizing, okay? So it's outside this set of self-maximizing shares. Okay, so I promised that I'll discuss this difference between dominant strategy incentive compatibility and self-maximizing shares. So in dominant strategy incentive compatibility, we assume that there is a fixed allocation algorithm, while in self-maximizing share, we are not going to assume that the algorithm is fixed or known. Actually, we only know that the agent is guaranteed to get at least her share. In dominant strategy incentive compatibility, it is best for the agent to report truthfully the valuation VI, fixing V minus I for any report V minus I, given the fixed allocation algorithm. While for self-maximizing, you get the best guarantee by reporting VI. That is, if you consider the worst algorithm and the worst case valuations of the others, then the share guarantee will be maximized by reporting VI. So we see that in a sense, these 2 notions are incomparable. They are not, it's not that one is strengthened the other, but rather they are incomparable. Okay, so now let's talk about domination. so basically, the MMS was very nice because clearly there is no share that is feasible that is larger than it, but unfortunately it's not feasible. So we can ask, is there some other share that is the best possible share? That is, we want a share that dominates every other share. So a share S dominates S prime if S of V is at least S prime of V for any V. That is, it always guaranteed the agent a larger valuation, a larger piece of the pie in a sense. And a share S, a feasible share S is a dominant feasible share if it dominates every other feasible share S prime. And you can look at a subset of the shares, and instead of trying to dominate all feasible shares, you can try to dominate only the self-maximizing shares. So these are a smaller group of shares. And a share S is SM dominant feasible share if it dominates every feasible share that is self-maximizing. So what we ask here, does there exist an SM dominant feasible share for the class of additive valuations and beyond? That is, if we can find an SM dominant feasible share, in a sense, we found some ideal share that is better than every other share that satisfies this condition that is called self-maximizing. And we also show in the papers that this condition implies monotonicity, it implies one Lifshitzness. So basically, it's a weaker requirement to dominate self-maximizing shares than, for example, dominate on monotone shares. Okay, so we are interested in this intersection of feasible shares and self-maximizing shares. Of course, this intersection is not empty because the share that is always zero is self-maximizing and feasible. There is no reason to lie. And it's easy to see that there are other shares that are feasible and self-maximizing. For example, if I give you the nth most valuable item, this is feasible to do because I can just do a round robin, letting each agent pick an item, and this gives an agent his nth most valuable item, and that share is feasible and it's self-maximizing. It is, of course, better than the zero share. And it's easy to see that there is another share that dominates this share, and we can ask, can we find some share, an SM dominant feasible share? That is one share that is feasible and dominates all the shares here in the intersection of the self-maximizing share and feasible shares. Okay, so let's discuss our result. The first question is there a share for a class of valuation C, say for additive valuations, that dominates all feasible shares, at least those that are self-maximizing? And we have a very strong negative result showing that for additive valuations and beyond, there is no feasible shares that dominates all feasible shares that are self-maximizing. That is, we are not going to find a share that is, in the sense, best. Okay, there is no share that is the ultimate feasible share, and therefore there will always be a space for defining different shares and considering the trade-off between the shares, the different shares. So it basically rules out the existence of SM dominant feasible share. Okay, so how do we, let me mention a few remarks about this result. So first, we don't require the dominating share to be self-maximizing, and still this impossibility holds. So we allow it to be just any feasible share. And secondly, this impossibility does not rely on computational hardness. So it is not conditioned on P not being equal to NP or any other assumptions like that. Okay, so in the paper, we actually present two proofs. One proof is explicit, and it's used picking orders. And since I don't have enough time, I'm not going to discuss it. The other is actually deriving this result from another result that I'll present next, and I think is of independent interest. So the result says the following, that if we have a share that is feasible, there is always some other share that is both feasible and self-maximizing that dominates the first share. So we can always find a better share that all is still feasible and is also self-maximizing. So this theorem basically says that in some sense, self-maximization is without loss of generality. I can always take a share that is feasible and move to another share that is also feasible and is self-maximizing. The only caveat is that this transformation is not polynomial time computable, not even for additive evaluation, so we cannot use it constructively to design self-maximizing shares. So I'm not going to prove this theorem, but I want to show you how this theorem implies the theorem that says that there is no ultimate feasible share. So what do I mean by no ultimate feasible share? I want to show that there is no share that dominates all feasible shares that are self-maximizing. Okay, so let's start with some additive evaluation VI and define a feasible share S of VI as follows. S of VI, when gets as an input VI, it equals to the MMS. And if it gets as input any other valuation, VI prime, that is not equal to VI, it is 0. So this is a very simple share definition. And of course, this share is feasible because if all the valuations are VIs, then by definition, we can give every agent her MMS. And if some valuation is not VI, then we are not obligated to give the agent anything. So we see that this S of VI is actually a feasible share. Now we are going to use the theorem that says that there is some S prime of VI that dominates S and is self-maximizing. So this is a feasible share that is self-maximizing and dominates S of VI. Now, of course, if we want a share S that dominates every feasible share that is self-maximizing, it must dominate S prime of VI for every VI, which means that it must dominate the MMS, essentially. And since we know by the result I mentioned that there is no, that the MMS is not feasible for 3 agents and additive valuation, there is no share that dominates every share S of VI. Okay, so this proves the theorem that for additive valuations, there is no feasible share that dominates all feasible shares that are self-maximized. So what do we do given this impossibility result? So we're going to relax the domination requirement, and instead of trying to dominate every feasible share, we are going to try to raw dominate every feasible share. What do I mean by raw dominate? So S raw dominates S prime if after scaling down S prime by a factor of rho that is smaller than 1, then S dominates S prime. So basically we allow the domination after scaling down the shares, and we want to find a raw dominating feasible share, a share that raw dominates every other feasible share. So an easy observation is that a share is raw dominating feasible share if and only if it raw dominates the MMS. Recall that the MMS is an upper bound on all feasible shares. So if you're able to raw dominate the MMS, you raw dominate every feasible share. So for example, recall that the 3/4 MMS is feasible. And of course, it raw dominates the MMS for rho equals 3/4. And therefore, it raw dominates, it 3/4 dominates every feasible share. Okay, so from now on, I'm going to focus on additive evaluation over goods and try to obtain a positive result. So we discussed the fact that the MMS is not feasible. And you might ask, why and I'm satisfied with 3/4 MMS because we know that 3/4 MMS is feasible. The reason I'm not satisfied with it is that 3/4 MMS is not self-maximizing. So recall this example that we have seen before, proving that the 3/4 MMS is not self-maximizing. So our goal next is going to find a raw dominating feasible share that is self-maximizing and also polynomial time computable. And of course, we want to do it for a rho that is as large as possible. Okay, so we add the polynomial time computability as another requirement, and we are going to search for a share here in the intersection of the 3 circles that raw dominates every green share. So every share in the feasible shares should be row dominated by the shares that will pick in the intersection of polynomial time feasible shares that are self-maximizing. So here is our main result. We prove that there is a share, which I'll discuss next, that is self-maximizing, feasible, and polynomial time computable, and it is essentially 2/3 dominating. So it is 2/3 dominating. The best that we know without the requirement for self-maximization is 3/4. Here we get 2/3. And if the number of agents is smaller than 4, we improve this 2/3 to 4/5. For 2 agents, of course, the MMS is feasible and self-maximizing, but it's easy to see that the MMS is not polynomial time computable. So if we want a polynomial time computable share that is self-maximizing and feasible, then we need to relax the goal, and we aim to get 1 minus epsilon, essentially a p-tas. So we have a share that is a p-tas. For every positive epsilon, it can give us 1 minus epsilon domination in a share that is feasible, self-maximizing, and polynomial time computable. And the main open problems that we leave is improving this 2/3 to 3/4 or maybe beyond 3/4, but 3/4 is a bound that we already know is feasible in polynomial time. But if we add this requirement of self-maximizing share, can we still get the 3/4? We don't know that, and we leave this open. So I told you that this positive result is based on a share that is called the nested share. Let me introduce this nested share.
Moshe,
So
just sorry to interject, but we are running over time. So if it's possible to end soon.
Sure. Yes, thanks. I'll just mention what is this definition of this share, and I'll wrap up. Okay, so the nested share, recall that the MMS basically think about all the partitions, all the possible partitions, and give you the worst bundle in the best partition. Now we're going to restrict the partition to have a specific form. So what form does it have? We're going to sort the items in decreasing order, and we're going to restrict bundles to be constructed. Each bundle, the first bundle is going to be constructed from some items in the prefix and some items from the suffix. After removing them, nested in them is the next bundle. The bundles that contain this item and these items, etc. So the bundles are nested, and this is why we call it the nested share. And we're going to add this parameter q that basically says that we want n minus q of these sets at the beginning to be singletons. And this is important for feasibility later. So our share that we're going to use is the nested share with parameter q equals 3, that basically says that if n is 7, q is 3, 4 of the first things are just singleton. So that's one bundle, and then the second bundle has only this item, the third bundle has this one and this one, etc. So the result basically says that this share, the nested share with parameter n and 3, is self-maximizing, polynomial time computable, and give us this 2/3 fraction of the MMS. And let me just say that this self-maximization is a generalization of this property of the MMS, while MMS is self-maximizing, essentially kind of a maximal in range argument. Then polynomial time computability comes from dynamic programming. This improved fraction is using computer-assisted proof that might be of interest. And the challenge in the proof is actually proving that this share is feasible. And that's the main technical part in the proof. So that's the main result. So let me summarize. We initiate a systematic study of feasible shares as a notion of fairness. We suggest self-maximization as an alternative to dominant strategy incentive compatibility. We show that any feasible share is dominated by a self-maximizing and feasible share, and we use it to prove that there is no ultimate feasible share, that is a share that dominates all the feasible shares that are self-maximizing, and this is true even for additive valuations. Then we relax the goal. Instead of asking for domination, we ask for raw domination, and we prove positive result proving a row dominating feasible shares that are self-maximizing and polynomial time computable for additive evaluations, and p-task for 2 agents, and some constant at 2/3 domination for any n, and an improved domination for n that is at most 4. So thanks very much for listening.
Right. Let's thank the speaker.
Thank you. So let me turn this off so I see you. I'll be happy to take questions.
Okay, so Adrian, do you want to unmute and ask your question?
Sure, actually, I think you answered it. I mean, the issue was when you started talking about it, it wasn't clear what the share guarantee was, as it wasn't unique. But then when you started looking at domination and stuff, I think that was clear that you meant
great.
Yeah.
Okay.
All right. Then I have a bunch of questions about self-maximization. Whether there is, have you thought of any characterization for self-maximizing shares? If there is a natural subclass of shares succinctly kind of represented, where you can check in polynomial time whether a given share is self-maximizing or not. Is there a natural subclass of shares that are all self-maximizing?
So these are great questions. First, let me touch the third question. Essentially, in this paper, we suggest a subclass of shares that are self-maximizing. And these are essentially, you can think of it as, MMS is like VCG, and the maximal in range mechanisms are similar to these shares. So instead of optimizing over all partitions, you first restrict the partitions, and then you do MMS on these restricted set of partitions. We call this ordered shares, and on these ordinal maximin shares. So on these shares, we can prove that all of them are self-maximizing, and both our positive result, the p-task, and the result for n larger than 2 are essentially presenting shares that are of this character. Now, I'm not aware of a characterization of these self-maximizing shares. I think that they are very natural. We're using them, the cut and choose is essentially the same, kind of spirit, right? Why would you cut the cake equally? Because you know that you choose second and the adversary will choose the best part first. So in some sense, this is a very natural notion. I don't have a characterization. And checking in polynomial time, yeah, so, my answer for the first question actually has, in the p-task, we have exponentially many sets there, but we show that we can compute them in polynomial time for this specific set of partitions. I'm not aware of a general result in that spirit. So great questions. Thanks.
All right. So yeah, let's thank the speaker again.
Thank you. Thank you very much.
And then we have a few announcements. Dominic, you want to make the announcements?
Thank you all for coming. I have an announcement about the steering committee of the seminar. We have a personnel change. Bill Zwicker is leaving the committee. He was instrumental in getting the seminar started. We had our first meeting in April 2020 during the very start of the COVID lockdowns. And Bill was pushing to get the seminar started so that the community could come together regularly. And I think this has happened since then, and it's still a wonderful seminar. So thank you very much for your service. Instead, Florian Brandl from Bonn is joining us, and thereby also keeping the disciplinary diversity on the committee as a mathematician / economist, I guess. Right, so welcome Florian, thank you Bill. We will have no seminar for the summer break in July and August, and then we will reconvene in September. I will email around a survey to decide on a weekday in case we can find one that is particularly good for many of us. And so have a nice summer and see hopefully many of you in Israel.
See you soon.
Bye.
See you in Israel. Bye. Thank you.
Bye.